find in the school books, in the newspapers, that use a von Neumann computer. Anybody knows what is a von Neumann computer?
Yes, sir.
Okay, so Ijazur Rahman, can you please tell what is a von Neumann computer?
It has a separate memory part and separate processor part, computing part.
Anybody can give a better answer? What is a von Neumann computer? Because this is the basic thing.
Yes.
Sir,
Yes.
sir, the instructions which are stored in instructions and data stored in the memory, which are then brought to the processor for execution, and after executing, the output is stored back into the memory. And in this type of architecture, we have the program memory and data memory as a single entity. They are not separate.
Okay. Okay. I think that's the right answer. Sohini said that here instruction is fetched from the memory. Instruction is stored in memory. It is analyzed and then processed based on the data that is stored. And then the next instruction is fetched from memory. It's analyzed and the instruction is carried out in the data and so on. But then you will say that what is great about it? That's what all of us do in every computer, that we instruction the programs from your first level C programming course. You know that program is compiled, executed, it gets stored in the memory, and instruction by instruction executed. So what is great about it? But just imagine the time that John von Neumann saw what was happening. Okay, we'll see what he saw. But then right now, just to put things in proper perspective, it does not happen like that actually anymore. It is not that an instruction is fetched, analyzed and processed, next instruction is fetched, analyzed and processed, because there are many things happen, including your laptop and desktop servers. These are now multi-core. Many instructions are fetched. Superscalar, even on a single processor, many instructions are executed, hyper-threaded, graphical processing unit, speculative execution, even before instruction is fetched, even if before previous instruction is completed, the other instructions start executing, called a speculative execution. But then these are all part of a advanced level course. In the first level course, we don't discuss all this. We discuss this in the next level course. Very unfortunate, because this is what happens in every laptop, desktop, etc. Unfortunately, we don't discuss in this first level course because we have to have the background, what really happened. A bit discouraging, isn't it? That we are discussing in this course what happened, not what is happening. But in any case, that will give you a good grounding on the computers, and you will be able to appreciate multi-core, superscalar, hyper-threaded, GPU, speculative execution, memory hierarchy, and so on. Let's see what John von Neumann did. 1944. Okay, 80 years back, not 90. In the older days, before John von Neumann, a programmer would sit in front of a computer. Let's see this computer. See there, the programmer is standing here. And what is he doing? He is executing instructions. How does he execute instruction? He flips switches here. Just like you do in the calculator, you enter instructions. You enter numbers and then enter instruction, and then the result gets stored. You enter additional numbers and so on, and then the instructions you enter. Here it used to happen almost like that, excepting that the data was stored. The instruction is entered by the person here through switches. And not only that, he had to not only press the switchboard, he has to sift through these cables. Do you see this cable? He will once in a while, he will also have to change the cable depending on IO and so on. But then John von Neumann, he was the first to get the idea that why enter the instructions manually? That is really slowing it down because of the manual entry of the instruction. Can't we store the instructions, encode the instructions, store in the memory just like data, and the processor would fetch the instruction, interpret and execute the instruction using the data that is also stored in memory. And from that day onwards, all computers became fetch, decode, execute. The programs could be stored. That was the big contribution of von Neumann, stored program computers. The programs could be stored just like data. And the program instructions are fetched, decoded, and then executed using the data stored in the memory. Big improvement. And that is what we are almost doing till now. Before we go further, just let me tell about this course, because finally as teachers we'll have to give a grade, and this year is a special year, this semester, having online, and we can't really hold exams etc. to be able to give you marks and grades. But then Professor Rao and myself, we discussed and we said that we will conduct continuous quizzes. The computer architecture part in our lectures, every 2 or 3 lectures, we'll have one quiz, maybe of 10 minutes or 15 minutes. And that constitutes 100% mark for the computer architecture course. So the quizzes will be done on this Microsoft Team itself, mostly MCQs, some computations. You have to enter the number, and then the class interactions. The online teaching, the one big hazard is that even if you have vanished in front of your computer or slept off, we have no way of knowing. And that makes the class extremely difficult for us teachers. We don't know whether what we are saying, is it being hard at all? Is there the student in front of the computer? Is not there? Don't know. So we have kept this class interaction, which is kind of a bonus mark. See here, it's adding above 100%. If you have interactions, you ask questions, answer questions, and sometimes I'll get your names here on the list and I'll ask names, and if the names they respond, we'll give these marks. And I have my notebook here. I'll note down the names and we'll give marks based on that. But then the online, as you have seen in the last semester, the grading is normally much more relaxed compared to an actual physical exam. So don't get too hassled. And we have deliberately kept this 10-15 minute continuous evaluation because we find that evaluation more than 15 minutes, etc., students have tendency to consult each other in internet, so on. So to reduce that scope, we give aggressive set of questions. Don't creep that, sir, questions are too many for 15 minutes, because everybody will have to answer those questions. And that is just to prevent you from consulting each other. I know that most of you are good, but then some will try to break through our exam process. We don't want to do that. So this is the scheme. But then one thing, that there were many who have applied from other departments for crediting this course for various reasons. Those who have background, they have done a digital logic, switching, etc., like the ECE students, we have approved all above 8 CGPA. But then for other departments, above 9 CGPA, we have approved, thinking that they will be able to manage read through if they don't have background. But for the students who are between 8 and 9 from other departments, just want to tell them that this course, they may find it a bit difficult if they don't have the background of digital logic, switching, etc. So with the word of caution, if they still insist, will register, because right now it has exceeded 175, as I was saying, might accept few students, I mean those who are really interested. But then this is the word of caution that might find it hard, don't want them to face hardship, might take other courses. But if you insist to put the effort, we will approve on the ERP. That is today. We'll approve it on ERP. But then this is the word of caution. Okay. Now this is the textbook for this part of the course. Computer Organization and Design, Patterson and Hennish, 5th edition. And this book has been uploaded on the team. If you see the folders there on the team, you will find one folder called as course material. In the course material, this book is available. I just collected the PDF of this and uploaded. And this book will mostly follow systematically, chapter by chapter. This is one of the standard books. But then what we discuss here is a superset of what is there here. Because this book doesn't discuss some aspects which we thought should be of interest in this course. So the book is available and the slides are a superset of this book. We don't use the book slide actually. It's a superset. And the slides will be uploaded in the slides folder. And also the recorded video for this course will be uploaded. In case somebody has network problem, did not some reason attend the class, should be able to look at the video. But remember that please attend the class, because there is this 5% extra mark on question, answer, etc. And also the quizzes will be done every 2-3 classes in the class itself, 10-minute or 15-minute quiz. So that's about the course book. Now let's start with some very basic fundamentals. Anybody has any questions so far about the grading, course content, how it will be operated? Professor Rao handling the operating system part independently. I am handling the architecture part. Any questions so far? Grading. Okay, is it? Okay, fine. Yeah, please.
Sir, so, hello.
Yes. Yes, please.
Yes, sir. I have a question. So, like, sir,
Yes.
sir, my request for the course has not yet approved, right? Like,
Will be done
sir,
today.
okay, sir. Actually, sir, I have already completed switching circuit like in the previous year. So, like, that's why I want to do this course.
Correct. So then in this course is okay for you. I will approve all the pending requests today. Just wanted to give this message that those who don't have the background, they might consider not taking this course. So, but those all the requests will approve today. Just now, just after the class, all the requests will be approved. Those who are above 8 CGPA.
Okay,
Any other?
Thank you, sir.
Any other question?
Sir, so the quizzes will be held on a weekly manner, right?
Yeah, see, today is Monday. So for the architecture part, we'll have the next class and then we'll have the quiz on next Monday. 10
Okay, sir.
minutes. Okay. Now we'll start with some very basics. we all know what is a terabyte, petabyte, exabyte. So how is petabyte defined or terabyte defined? How is a terabyte defined? Can anybody tell? Yes, terabyte. How much is
The
terabyte?
the decimal terms are defined with powers of 10, whereas the binary terms are defined with powers of 2. For example, 1024
How much is petabyte?
bytes
That's
is 1
Ambuj.
KB byte.
Ambuj, my question is how much is a petabyte?
1000 tera.
How much?
1000 tera
Tell
is
me, 10
10
to
to
the power
power
how much?
15.
1024. 10 to the power 2 to the power 10.
And how much is a gigabyte?
2.9.
10 to power 9.
Okay. So more or less, I think everybody knows that. But those who don't know, originally kilo, mega, giga, tera, peta, etc. are used with decimal base. 10 to the power 3, 10 to the power 6. And let me just tell you one incident. I was invigilating one exam here in IIT. Not this course, but another course. And then there was question on gigabyte. And then he was a BTech student actually, final year. And he asked me how much is a gigabyte. So anyway, so you know you are better off than him. And so this is base 10, 3, 6, 9, 12, 15, 18, 21, 24. But then on the other hand, the binary system, we have 2 to the power 10 roughly corresponds to 1000, only 2% larger, 1024. A maybe byte is the actual term for the binary, which is 2 to the power 20, 2 to the power 30, 40, 50, 60, etc. But then we loosely call them kilobyte and so on, even though we mean it binary, 2 to the power 10. We still call it kilobyte, megabyte, etc. But then if you look at the actual notation, this we should call as kibibyte, maybe byte, gibibyte, etc. And write as KIB, etc. And capital B is for byte, small b for bit. And initially it is 2% larger. 1024 is 2% larger than 1000. And if we look at the megabyte and maybe byte, it's 5%, 7%. And it is, if we go to the yottabyte, it is 21%. And of course, don't have to really explain that why it is becoming, the difference is becoming larger because of this power thing. Okay, so let's look at some basic thing. One is that the computer has progressed phenomenally, starting from the time of von Neumann. And the progress of the computers has been captured by Moore's law, basic law. If you tell that you know about computers, somebody might tell you that please tell us Moore's law, or he will give you a small problem and say that how much will it come out Moore's law. Some of you possibly know Moore's law. We'll just discuss today a little bit about that. The law is a bit tricky actually. We'll come to that. And because of this improvement in computers, now the computers are there everywhere. In automobiles, in cell phones, World Wide Web, search engines, and whatever application you name, now it is all computer driven. And that is the reason why engineers from all disciplines need to know about the computers, because they will be using this. We are now looking at the introductory chapter of the book. First chapter, you will find the exact same things. Please read up after the class. because some parts the book not captured here in the slides, and also slide has some parts that are not there in the book, but you will find this class of computers etc. in the book. The personal computers and the servers, what is the difference? Can anybody tell how is a server different from a personal computer?
Sir, the server has a very large storage.
So this is others. Others says server has a large storage. So if we attach a very large storage, terabyte storage to our desktop, will it become a server?
No, sir, it also needs to be connected to a network. Like we access from our personal computers, if we access a Google, then we are accessing Google server.
Sir, we access server remotely from a
Anyone else?
Sir, servers are basically for multiple users accessing a single computer.
Server is designed to handle requests from different computers.
So they need to handle different requests from different users, and one of the things is personal computers need to have a GUI, a display. Servers don't necessarily need that as well.
Let me just ask the question in another way. That where is a server used? Can you give an example of a server that you have seen?
Where high computation
Email
is
server.
needed.
Web server.
Sir, high
sorry,
computation.
IIT KGP server.
Any network-based application.
Sir,
so
where
Bipul,
high
Yeah, sir,
computation
like-
is needed.
let me just answer
Sir, AWS
by
is
one. Bipul,
working
you
on
take your
servers.
answer. Bipul, what is Bipul?
Yes, sir. Any network-based application basically requires a server. Any network-based
I mean,
application.
why? What does the server do?
So the server handles incoming requests and just processes them according to the needs of the what basically does whatever the application does, processes the request and gives out responses.
No, just give me an example of a server where you have used a server.
Or in hosting a website.
Any website you go has to be hosted somewhere. So for example, if you are hosting a
Okay, web server. Web server. Web
Yeah,
server is one example. Yes, web server. Any other example?
Sir, ERP.
Okay,
ERP is hosted onto a server.
application
So
server.
that is essentially a web
Yes, sir.
server.
Web server, email
That is
server.
essentially a
This
web
is
server.
Okay.
So many offices have local work servers for saving their informations.
So game server.
Okay. Network servers and so on. So
Database.
the personal computers, they normally used for variety of applications. On one hand, we do word processing. On another, we look a small video. We have this video conferencing. We do Excel. We listen to music, etc. So the personal computer is used for variety of application and also cost performance trade-off. On the other hand, the servers by definition is that many users access the servers through a network. Large number of large number of users request service here. The servers provide service, maybe file service, maybe email service, maybe application service, and so on. So compared so the servers have high storage, performance, and reliability. So basically, we have a powerful CPU. Typically, we have 8 or 16 core processors, high memory, and high storage, and extremely reliable because thousands of users access it. We don't want it to be disrupted. But also we have the supercomputers and the embedded computers. The supercomputers, they do high-end engineering calculations. And these are a small fraction of the overall computer market. Only few supercomputers are there. On the other hand, embedded computers, these are largest in number, much larger than the desktops, laptops, supercomputers, servers all together only constitute about 10%. The embedded computers are 90% of the computers in use. Most of them, we don't realize them because they are hidden in parts of a system. For example, the computer mouse, we think that we are operating a mouse, but then inside there is a processor. And that's a computer. And these have stringent power, performance, cost constraints. If you look for the embedded computers, you'll find many of them in your phone, cell phone, in a tea making machine, in a laser printer, and so on. The PC, this is again taken from the book. This is again taken from the book. So somebody has taken the control of this. Don't do that because this is disrupting the class. So don't take control here. Maybe I should override your control.
So you can make everyone attendee so no one will be able to take control.
Yeah, I think we'll do that. I'll next class onwards we'll make everybody attendee so that this disruption does not happen. Because now somebody is able to mute me and so on. Okay. So the other computers used in other applications are increasing much more rapidly, and this is old data in the book, but then they have really overwhelmed the other applications. Now let's come back to this Moore's law that we are discussing. Somebody will ask you someday, and of course we will be asking that anybody knows Moore's law? Just let me get, anybody knows Moore's law? Very famous law. There in school books also, 1965, very old law. And this law, yeah, anybody would like to answer?
Sir,
Yeah,
The number of transistor per square inch will keep doubling after certain period.
so after a period
Sir,
of
in every
18
machine.
Abhijay Mitra. So you are saying that number of transistor doubles every how many years? 2 years.
So probably, sir, within 1 year and probably 6 months, 1 year and 6 months, or maybe something.
Okay, let's
maybe 2
look.
years also.
Okay, so somewhat like that. Let's look at it. So initially in 1965, Gordon Moore, the founder of Intel, he said number of transistors per square inch roughly doubles every 18 months. But then after 10 years, he revised his statement. He said, no, that's too ambitious. It doesn't really double every 18 months. It is actually 2 years. And from then onwards, this has held that the number of transistors is doubling every 24 months. It's not exactly a law, but then it has held good now for about 55 years. And what he said is that the transistor density, this was the actual statement, that the transistor density of a minimum cost semiconductor chip would double roughly every 18 months. In 1965, that's the statement he gave. Transistor density of minimum cost semiconductor. But then the question comes here that what is a minimum cost semiconductor chip? And then with his law, it is implied that transistor density is correlated with the processing speed. But then why should transistor density be correlated to processing speed? I mean, if we have more transistors available, double every 18 months, how can the processing speed improve? Can anybody answer this question? That how can the processing speed improve with transistor density?
So we can put more transistor in a space, and with more transistor.
Could not hear. Manideep could not hear your answer.
Sir, a simple example would be a DRAM and an SRAM.
But
Sir, since we have some space, we can fit more transistor into the space, and so you can do more computation.
How? No, that is my question. You have more transistor. How can you do more computation? See, if it is a adder or a subtractor or a multiplier or so whatever, you need some number of gates. If you are given millions of gates, what will you do? How will you?
So, for example, memory implementations can be changed. Like in a DRAM, one transistor is used and it is comparatively slow than an SRAM, which uses basically 6 transistors. So within a short period of time,
assuming that whatever you said is correct, what will you do if you are given more transistors? You said 6 times transistors needed or whatever, but then what will you do? Still more transistors are given to you.
We can do the things in parallel.
Is this because of parallel processing and all?
Parallel computation.
So like multi-threading can be done more if there are more transistors.
Physically, I would be able to fetch data faster if I have more transistors. Like
How you fetch data faster if you have more transistor? How does it help fetching data faster? See, you have to give answer with reasoning. That this is how
inputs will increase. Higher frequency when size is
Sir, by changing the clock speeds of individual overall circuit.
That why don't you do with small number of transistors? That you can do, isn't it?
If we have more number of transistors, we can allow higher bit processing. Like my processor can be a 64-bit processor or 128-bit processor.
Assuming that you have a 64-bit processor and you're given more transistors, what will you do? Make it 120.
Then we can do parallel. Then we can do parallel processing.
Okay, not clear. Answers are not clear exactly. We'll see what really happens. Please watch out for this. That how is the processing speed improved with more transistors? Very fundamental question.
Hello, sir.
Yes.
Sir, can we do using pipelining so that we can reduce the critical delay? So that we can improve.
Pipelining does not need Sohini. Let me just clarify. We'll see pipelining in this course, but then pipelining does not need more transistors. It is pipelining is about keeping the transistors more busy. It is not about requiring more transistors. So I don't think that answer is correct. Let us see. You please watch out in this course as we proceed. This is a fundamental question. How is the availability of more transistors going to improve the processing speed? We'll answer in this course. And as you can see here, the Intel processors, starting with 4004, 8080, etc., the processing speed, no, this is the transistors on the y-axis. This is a log scale. Look at the y-axis, which is a log scale, and the x-axis is a linear time scale. And this is a straight line here. In the Intel microprocessors, what happens? And even though it looks like a straight line, it's actually an exponential increase. Every 2 years, it is increasing as per Gordon Moore. It's a straight line, appears straight line just because it is a log scale on the y-axis. But then another very fundamental question here. Let me see if anybody can answer this. That the processor performance is becoming twice as fast. We will show the performance figures now. That you will see that the performance is becoming almost twice every 2 years. But then the memory capacity is increasing much more rapidly, twice as much after every 18 months. How is it that the memory, see the transistor, same transistor is being used, right? So how come the memory capacity, like the RAM ROM, etc., that you are getting is increasing much more rapidly. The cache memory, RAM, and so on, increasing much more rapidly compared to the processor performance. Can anybody answer this question? Why?
So memory is a very regular structure, whereas for a processor, there is a lot of irregularities.
Sorry, I could not hear. Repeat, please repeat your answer.
So the physical structure of a memory is very regular.
Okay.
But in a processor, there are a lot of interconnects and a lot of complexities. So.
Okay. Okay, I think I'll take that answer. So Ambudj, good. You could answer that. I think that is what I was also going to answer. That the memory, we'll see that these are regular. The DRAM, if you look at, it's a very regular structure, whereas processor is irregular. Even though you have lot of transistors available, I mean, you can put on the chip, you cannot really use them. So the memory improves much faster. Okay, I think we have to do something. Somebody has again taken control. I think next class I have to do this, that make you all attendees. Otherwise it's becoming a problem. Today class don't do, please anybody don't take control having problem here. Getting disrupted, inconveniencing everybody including myself. So please don't do today, and next class will take care, just make everybody attendee. I just forgot to do that. Okay. But then let's just try to understand what he meant by the minimum density transistor. The minimum density transistor means that the density of transistor at which the cost per transistor is the lowest. So that means there must be some contradictory influence on the cost. The contradictory influence is that as we put more transistor on the chip, the cost definitely reduces, but then the chances that a transistor is bad also increases. So given a technology, there is a density that we can manufacture. If you try to put more transistor, the transistors will become very unreliable. The number of defects will be more chips will have to discard. If we look at the internal of the chip, looks like this. And let's see how this minimum cost is defined here. The IC cost is the die cost plus testing cost plus packaging cost and divided by final test yield. So in the test, if we have to discard 50% of the chips, then the IC cost is twice of the die cost, testing cost, and packaging cost. After we test the chip, we find that some are bad, we throw them. So if 50% is bad, our cost here doubles. If we look at the manufacturing process, we find that we get a silicon ingot, slice it, create wafers out of it, and in the wafer we have these processing steps through which we have these patterns, and each one of these becomes a chip. And then on this we have the circuit which is etched through these 10 to 20 to 40 steps, and then we test it, and then we discard some of these bad, see the crossed one are the bad dice, and then we package the dice and finally test it and discard some of the tested packaged dies also. So this is the silicon ingot is being drawn here, We got the silicon ingot and sliced it, got this wafer, and on this wafer we have these patterns, circuits etched, and finally we get these dies out of it. These dies are made into the chips. So the IC cost is die cost, testing cost plus packaging cost divided by final test yield. It's in that. The die cost, if we look at this first term, the die cost, it is the total wafer cost divided by how many dies are there. Dies per wafer, how many dies per wafer into die yield. That is how many good dies are there. And of course, these parts that are outside here, these are not full dies. They have to be discarded actually. And then we have this process, VLSI manufacturing process, through which we have 10 to 15 mask layer. The first half a dozen or so, they define the transistor, and the top half a dozen, they define the interconnect on these transistors. And look at this, that based on the Moore's law in 1975, he said that it is not really, and this is log scale actually. On the y-axis is log scale transistors per die, and the time here linear scale. And this straight line that you are seeing here is actually twice per year. It's exponential, but because of the log scale, it's appearing straight line. And then he said 18 months. Sorry, initially 18 months and then 2 years. But see here, the red ones is the memory is increasing much faster than the processor. The density of transistors in the processor is much less than the memory. And we know why the density in the processor is less than the transistor in the memory. And look at this. This is the performance. The other one, we are looking at the transistor, number of transistor density and so on. But here we are looking at the performance of the computer, Intel computer. No, not Intel, there are various computers here, AMD, Alpha, etc. And look at this. This is also taken from the book. And see here, initially it was rising very slowly. Even though the number of transistors were increasing as per the Moore's law, but then the performance till 1984 was very low. See here, a very small slope here. And suddenly in 1984, the slope became very steep. Performance increased very fast in 1984. And that was the year when the VAX 11785 was introduced, and that had poor performance. And suddenly the performance improved 52% per year. So that means twice per year. Per 2 years it doubles. That's how the performance has also been increasing. And of course, of late, it has performance improvement has slightly slowed down. But why was this 1984? What happened there? We will see in part of this course something called as the RISC processors. The VAX was the CISC processor, and just 1984, the RISC processors were introduced, and then there many things happened actually. We'll look at some of them, and then towards 2002, we could have large number of transistors, and they wanted to increase the performance the same way, but the transistor burned actually. The chip, when they tried to operate the given clock frequency, it burned. They found that heat generation is too much, and then they had to do something there, but then the performance is slightly tapered here. So this inflection point here is the risk. Now let's see that the performance has increased almost twice every year. But where from has the performance improvement come? One is number of transistors. And then if we have number of transistors, we'll see that what do we do with those transistors? We have memory inside the processor. Earlier it was not possible, cache memory, and then we had larger caches. And they help actually, having larger caches, they help improve the speed. And then faster logic. Very surprisingly, as we reduce the transistor size, the speed of the transistors also increases. The leakage currents, they increase as we reduce the transistor dimensions. The leakage current increases, but then the transistors become faster. We'll see that briefly, how it happens. And the other component in processor improvement, processor performance improvement comes from the organization, which is in the scope of our discussion in this course. The technology we are not discussing. That's part of a VLSI course. The processor organization, okay, they will not look at the deep pipeline and parallel execution unit. We'll look at the basic ones. And then the instruction set architecture. We'll look at this, the RISC architecture and the CISC architectures. How the RISC made it fast, the multimedia extensions, explicit expression of parallelism, and then the compiler technology has also played its role, finding parallelism in code and getting optimal code for the processor. The improvement due to transistor manufacturing has slowed down since 1980s. One of the major cause of concern is the leakage current. The small feature size gives to increased resistance, capacitance and propagation delays. These are all negative here. Even though we have more transistors, we have more heat loss. And also the biggest story is the leakage current. And all these things, resistance, capacitance, leakage, these are all contributing to larger power dissipation. We'll see the next slide that how are they increasing the power dissipation. And the other thing is propagation delays. As the length of the wire increases, becomes thousands of kilometers inside. If you look at the interconnect, if you reduce the size and put more transistors, then the length of the interconnect is extremely high, and we have these propagation delays and phase shifts. So that's also a very annoying problem. Now let's talk about this power dissipation. What is the power dissipation on a laptop or a desktop? Can anybody answer this question?
Sir, for a desktop it is for a laptop it is 35 to 40 watts.
Okay, Devraj says 35 to 40 watts. Anybody want to refine the answer?
i9, Prof. i7 or an i9.
Anybody wants to refine the answer? If you look at the power rating, now if you for your laptop you will find 65 watt is the power rating. On a desktop it is much more, but then it is in the year 2021. If you look at 10 years back, the computers used to consume power in terms of 150 watt. That was the rating. And 150 watt, remember that you make tea on a heater which has 500 watt. A induction heater has less wattage. But then see, the processor is consuming 150 watt. And induction cooker is also consuming like 250 watt or something. So you should be able to make tea on your processor. So roughly about 10 years back, it was much more, 100 watt in use and 40 watt idle. And now, of course, in recent years, it has reduced to some extent. We'll see the reason why. So the power dissipation is a big problem. As the technology improves, we have this feature size reduction. And we see here that the dynamic power is basically a switching power. We'll see what is switching power. And this is the leakage current. The leakage current now has overtaken the dynamic power. We'll see the switching and the dynamic power. Today we are at the end of the lecture. We'll stop here with this thinking, with this thought for you, that how come, what are these dynamic power and the leakage current? And this has become a big problem, and the performance improvement it has hampered for the computers. They cannot pack that many transistors, and also they cannot switch that fast. We actually switch off part of the processor as we go on. We'll see. We'll stop here unless anybody has a quick question. So we'll meet on Thursday at the time is given 8, I think. So we'll stop here. On Tuesday, Professor Rao will take the class. Okay, thank you.